Got a couple problems for you off of your number 9 homework CBA review. Starting on this one, it's number 2. It says how many protons are in an atom of, we have boron and it's 10. Okay. Remember, whenever we're looking at protons, protons are always the atomic number. So when we look on the periodic table, it's the number above the symbol on the periodic table, and boron has a 5 above it, so we know that it has 5 protons, because the atomic number always equals the number of protons. All right, guys, working on number 4, it says there are 4 naturally occurring isotopes of the element chromium. The relative abundance of each is, and it gives us, we have the percentage that are over here, and we have our AMUs that are by the side. It says find the average atomic mass of chromium. Now, one thing I will tell you guys, when you have it like this, if it gives you the AMUs, you're going to be multiplying these two guys. Okay, if it doesn't give you your AMUs, just use the mass over here. Okay, use that mass right there. It's basically the same number, but we know that AMUs are more precise. So if it gives you the AMUs specifically, use those. So all we're going to do here, remember when we're working these out, that the main thing we have to do is move the decimal over 2 places. So we move our decimal over 2 places on each of these guys. And this one we get 0.04345, and we move this guy over 2 places, and we get 0.83789, and then we move this over 2 places, and we get 0.09501, and move this over, and we get 0.02365. And what we're going to do is just basically we're going to put it in the calculator exactly as you see it, and we're just going to add each one of these guys up. So we're going to put parentheses around these guys right here, and then we're going to add in between them. Okay, and as we plug this in the calculator, all we do is just go open parentheses 0.04345 times 49.946044, close parentheses, add, open parentheses, write that, close parentheses, add, open parentheses, and just keep on going down. And the answer that you should get should be 51.996 AMUs, which that would be our average atomic mass. All right, guys, moving on to number 5. It says how many moles are there in 4.06 times 10 to the 23rd fluorine atoms? Now, whenever you see atoms and you're dealing with moles, you're always going to use the statement of equality or a conversion factor where 1 mole equals 6.022 times 10 to the 23rd atoms. Okay, remember that atoms and molecules, we can interchange that word, but for here we have atoms, so we put atoms. Now remember, when we're working these out, we always start with what the problem gives us. And we see that the problem gives us 4.06 times 10 to the 23rd atoms. And since we're starting with atoms, we know that we're going to end up dividing. If we start with atoms, we're going to divide. If we start with grams, we're going to divide. If we start with moles, we're going to multiply. But here it says how many moles, so we're not starting with that. So all we do is we put our atoms on the bottom so that we can divide. We put our 6.022 times 10 to the 23rd atoms, and that equals 1 mole. Okay, and specifically this is of fluorine. The math is still the same, so what we're going to end up doing is we're going to end up putting 4.06 times 10 to the 23rd divided by 6.022 times 10 to the 23rd. Remember, when you're putting it in the calculator, it should look like this: 4.06 second comma E 23, all divided by 6.022 second comma E 23. Okay, so that second comma is going to give us that E. You don't have to actually press the E, but you go second comma, that gives you the E, and we see that the answer that we should get is 0.674, and that should be moles, moles of fluorine. All right, guys, working on number 7, it says what is the mass of 16.9 moles of the element nickel? Now, remember, we said earlier that whenever we start with moles, we're going to be multiplying. So that's the first thing that we should see. Hey, we're multiplying here. And it's asking us, what is the mass? Now, anytime it says mass, you will need to use the molar mass. Okay, we know that 1 mole of anything, so 1 mole of nickel, okay, is going to equal the molar mass of nickel. And we find the molar mass of nickel by looking on the periodic table. And when we look on the periodic table, we see that it's going to be 58.69. So that means that 1 mole of nickel equals 58.69 grams of nickel. Okay, so all we got to do here is we set it up. Remember, we always start with what the problem gives us. It gives us 16.9 moles of nickel. Okay, we set it up. Now we know we're going to end up multiplying, and we look here in the moles right there, so we're going to put that on the bottom, 1 mole of nickel. That matches up, mole, matches up. Okay, so all we do is we put the rest on top, and we put the 58.69 grams of nickel. And these units will cancel out, and all we do is we multiply our 16.9 times our 58.69, and we should get an answer of right around 991.86, and that would be grams of nickel. All right, guys, on this next one, it says determine the mass. So anytime we see mass, we're going to be dealing with grams of 4.1 times 10 to the 23rd atoms of chlorine. It also says atoms. So it says mass and it says atoms. We don't see any moles in here. Okay, so the main thing here is we're going to use both our conversion factors that we used before. We know that 1 mole of anything, in this case it's chlorine, is going to equal Avogadro's number, 6.022 times 10 to the 23rd. Okay, and that's atoms. And we know that 1 mole of anything, in this case chlorine, is going to equal the molar mass, which that comes from the periodic table. And that's going to be 35.45 grams of chlorine. Okay? So these are the 2 conversion factors that we're going to be using. Remember, we always start with what the problem gives us. It gives us 4.1 times 10 to the 23rd atoms of chlorine. Now remember, I said before, if we start with atoms, we're going to end up dividing to begin with. So if atoms is on top, we need to divide, so we got to put our atoms on the bottom. So we put our 6.022 times 10 to the 23rd atoms on the bottom equals 1 mole. We put the other side, so we put this side, we put this side on the bottom, we put that side on the top. Okay, so now we set it up and we look, yeah, we divided, but we only got it into moles of chlorine, and we don't want our answer in moles, we want it in grams. So this is a 2-step problem, so we keep going. We used our top conversion factor, so if we use it, it's done. And we see that we have moles on top. Well, if we ever start with moles, what are we going to end up doing? Multiplying. So we're going to put our 1 mole of chlorine on the bottom, which we get from right there, and we put our 35.45 grams of chlorine on top. And we'll end up multiplying. Now to work this out, it's pretty simple. Just multiply the top and divide by the bottom. So 4.1 times 10 to the 23rd times 1 times 35.45, and we get our answer. And then we go divided by 6.02 times 10 to the 23rd times 1. Okay, and we should get an answer right around 24.1357 grams of chlorine. Okay, it's a 2-step problem, but remember, we basically do the same exact thing. It's 2 problems. Here's our first problem, right there, and here's our second problem. All right, guys, moving on to number 11. It says, what is the correct electron configuration for magnesium? Okay, we see that magnesium is right here. It's on the 3rd row. So we got to figure out our electron configuration for it. Remember that we have our S block over here, we have our F block right here, we have our D block right there, and we have our P block right there. Okay, so all we need to do is just start counting. Remember that the S block follows the rows, so this is 1, 2, 3, 4, 5, 6, 7, and so does the P block. Okay, so we're going to go 1s1, 2. So 1s2. Then we come back over here because we ran out of room, and we go 2s1, 2. Then we go all the way over, and we're on the second row still. And we go 2p, 1, 2, 3, 4, 5, 6. So 2p6. Then we come over here, and this is 3s1, 2, and we got to magnesium. So there is our electron configuration for magnesium. Remember, if we want to look at the total number of electrons, we can add up all the superscripts right here. But if we want to look at the valence electrons, we have to add up the one in the outermost energy level, which the highest energy level is going to be 3. So we box all the 3s, and we have 2 valence electrons. Okay, guys, it says write the electron dot notation for the element phosphorus. Remember, when we're dealing with, this is phosphorus. But remember, when we're dealing with electron dots, that we need to make sure that the dots represent the valence electrons, so we can't put any other electrons beside the valence one. Remember, valence electrons come from the outermost energy level, and the maximum number of valence electrons that we can have is 8. So the first thing we need to figure out is the electron configuration for phosphorus before we can move on. Okay, that is 1s. We start with 1s2, 2s2, 2p6, and then we go 3s2, and then we go 3p3. So the outermost energy level that we're going to have are the 3s. So we box all the 3s, we add those guys up, and that means we have 5 valence electrons. So when we look at phosphorus to write the electron dot, we put phosphorus. Remember, we always put 2 together, and then we spread the rest out. So we have 5, so I'm going to go 1, 2, there's 2 together, and I'm going to spread the rest out. And I go 1, 2, 3 for a total of 1, 2, 3, 4, 5. Okay, remember, 2 together, and then spread the rest out along the symbol. And this would be the correct electron dot for phosphorus. Alright, guys, looking at a nuclear equation. Remember, the main thing we're focused on here is the top numbers have to add up on one side of the arrow, and they have to be the same on the other side. So we look over here, and we see we have a total of 42 for our mass number. It's on top. We don't have anything else with it. So on this side, we have, not 42, but 142. So on this side, we have to have 142 as well. So what we do is we just take it. We already have 142, so we go 142, because that's what's on this side, minus what we already have, which is 142, and we see we get an answer of 0. So when we're looking for that symbol that goes right there, we know that the mass number is going to be 0. If we look at our atomic numbers on the bottom, okay, here we have 60 over here on this side of the arrow, and here we have 61. So we do the same thing. This is what the number we need. This is how many we actually have. And we go ahead and subtract them out. 60 minus 61 gives us -1. So in our symbol, it's going to be 0, -1. And anytime we have this, it's going to be a beta particle. And we put a little e there because it's an electron. And that should be the symbol that goes there, because we know that anything that has that capability of changing that proton into a neutron is a beta particle. All right, that's the answer for number 16. All right, guys, finishing up, we see we have, it says determine the frequency of light with a wavelength of 1.672 times 10 to the -7th centimeters. Main thing, whenever we're dealing with light, anytime we're dealing with light, these are the 3 equations that we're going to use. You can find these on your formula chart. Okay, it gives us the wavelength, and it asks for frequency. So the only equation that uses wavelength and frequency is our very first one. Main thing about wavelength, it has to be in meters, so we need to convert this to meters. So we have 1.672 times 10 to the -7th centimeters. And we know that 1 meter equals 100 centimeters. So what we're going to end up doing is dividing by 100. And we should get an answer of 1.672 times 10 to the -9th meters. And from here, what we're going to do is we're going to take this and we're going to plug it into the equation that we have where we have the c, which is the speed of light, equals frequency times wavelength. When we use that equation, remember that c is the speed of light. The speed of light is always equal to 3.0 times 10 to the 8th, and that is meters per second. Meters per second. And when we plug this into the calculator, we're solving for f. So to solve for f, we divide both sides by wavelength, and we get frequency equals the speed of light divided by wavelength, which is 3.0 times 10 to the 8th, all divided by 1.672 times 10 to the negative 9th. When we plug this into our calculators, remember we press 3.0 second comma 8 divided by our 1.672 second comma negative 9, and we should get an answer right around 1.794 times 10 to the 17th, and frequency is always in hertz.